graduate student here at UCSC. I've been doing this work in collaboration with Joel, Peter, Aldo, Doug Hellinger, Avishai, and others. And so I'm going to be talking about dark matter halo mass loss, and specifically touching on tidal stripping and the relaxation process following mergers. But first, I'm going to just quickly go over a different paper that I wrote last year and just give a little advertisement for this. And this was focused on studying the properties of how the properties of dark matter halos relate to their local environment density. So working with basically same group of people. So just quickly, what we did was we looked at central halos in the Bolshoi-Planck simulation, and we computed the density smoothed on many different scales around every halo, and then looked at how these different densities correlated with some of their properties. So, for example, if I draw your attention to the left column here, this is looking at a halo masses of about 10 to the 11.2. And we have on the x-axis the density around the halos plotted against what their concentration, spin parameter, and specific accretion rate were. And so what we found was just that in the very lowest density regions, halos had higher concentrations and lower spin parameters compared to those in roughly median density regions. And this is about a 30% difference for those all the way in the very lowest density regions. So furthermore, if again looking at the lowest mass spin we have here, this is looking at the so if we look at halos in low density regions at redshift 0, and median and high density regions at redshift 0, and we follow their progenitors back, plotting the median value of different halo properties for these groups of progenitors, what we see is that halos that were in low density regions at redshift 0 have always experienced lower tidal forces and always experienced lower and always had on average lower spin parameters. So they have lower spin parameters at redshift 0, but this is also true as far back as we can track them. And so our explanation here is just that these halos in the low density regions had fewer neighbors to spin them up as they formed and evolved. Okay, so now moving on to the main topic here of halo mass loss. So first I'll just give a little bit of motivation for why we're looking at this. So how common is it for halos to lose mass in the first place? Well, if we look at a plot here, so we've got on the x-axis the percentage of mass that a halo has at redshift 0 compared to whatever its peak mass was. So how much lower is its final mass compared to its peak mass, and this is what how we're describing the amount of mass loss against just the cumulative distribution function. For halos that are again mass 10 to the 11.2, we see that about 22% of these halos have lost more than 5% of their mass. So 22% of all halos of mass 10 to the 11.2 have lost more than 5% of their mass. So that's a lot of halos in our simulation. We can also look at this for the higher masses of halos, and it's less, but it's still a lot of halos, more than 10%. So maybe roughly 15 to 20%, depending on the mass of all halos, have lost more than 5%, and these are the ones that we're considering to be halos that have lost mass versus not lost mass as far as our analysis goes. So as far as what is causing the mass loss, we have two primary mechanisms that we've identified. So if we look at all halos that have lost at least 5% of their mass, and we group them into these different categories, what we have is what we're calling relaxation, which means that these halos had a major merger followed by and then subsequently relaxed and experienced some amount of mass loss. Those halos are in this group right here, and this is the dominant group. This is the most common variety. We also have tidal stripping, and this is more common for the lower mass halos, very not common for the high mass halos. And some halos can have both of these processes happening, which just basically means that they're both in a high experiencing strong tidal forces and have had a recent major merger. So we can't necessarily distinguish easily between them. And then the neither is where some halos have lost mass but haven't had a recent major merger or are experiencing strong tidal forces. And so we think the neither group is mostly just halos that have had a recent minor merger that's just below the threshold for the major merger mass ratio. Okay, so as far as the consequences, so if we look at spin parameter on the y-axis here against how much mass halos have lost, what we see is that there's actually a reversal in the trend here. So starting with halos that haven't lost any mass, as we go towards those that have lost a little bit, here we see an increase in the spin parameter for these halos, followed by a decrease for significant mass loss. And so what's going on here is that the this hump here is demonstrating what's going on to halos that have had a major merger and this subsequent relaxation type of mass loss. These halos tend to have an increased spin parameter from the merger. It's decaying back down, but hasn't decayed all the way back to the value that you would have for halos that haven't lost any mass. And this is a very common, this is the most common type of mechanisms that we're looking at here. And so it's dominating this sort of regime of about 5 to 20% mass loss compared to the other end of the plot here, where we're looking at where we're seeing a dominance from tidal stripping. This is very rare to have this level of mass loss from following a major merger, and so this is mostly just due to tidal stripping, which can cause very dramatic amount of mass loss. So for the higher mass spins, we see something similar, except that the higher masses are less commonly tidally stripped, and so we don't see as much of an effect from the tidal stripping. Okay, and so then I just lastly want to run through two examples, one of a major merger scenario and another of a tidal stripping scenario, looking at individual halo and how it evolves and its various properties are changing as over this time. So we've got a major merger for this particular halo. Right here, what we're looking at is 1 plus z on the x-axis, and time is moving to the left. So we've got mass, virial radius, Vmax, scale radius, spin parameter, prolateness, which is the shape of the halo, how elongated it is, tidal force, x-off, which is the difference between the center of mass of the halo and the highest density point, and then the virial ratio. Right, and then the mass loss is occurring right here following the major merger. So we have an increase with the merger, the subsequent loss here, and then it starts accreting again. So what typically goes on in these scenarios, and this is a fairly typical scenario for one of these types of halos with the merger and subsequent mass loss, is that we get an increase in many of these parameters right at the merger, followed by a slow decay as the halo relaxes. So some of these parameters also have 2 peaks here, and so mostly scale radius, the shape, and x-off, and that's just, we think, as a result of the incoming halo passing through the center, splashing back, and that's the type of response that we see, and we'll see that more clearly in just a minute. As we look at the particle distribution for these halos, just to get a little bit of a better idea of what's going on here. So these are all of the particles associated with this particular halo at redshift 1.4 about. And so we've got the magnitude of the radial vector of each particle on the x-axis versus the velocity vector of each particle on the y-axis. And then additionally, we've colored the particles by the redshift that they were first accreted onto the halo. So this blue is going to be more recent, and the darker blue is going to be earlier. And then additionally, the open circles, like here, there's only a few of them on this particular shot, but these are particles that are not going to be part of the halo at the final time step, so they're going to be lost at some point. So we've got the scale radius, virial radius, and Vmax indicated on here, as well as a distribution of the velocities for both all the particles and just those that will be lost at some point, as well as the density profile scaled by r cubed down here, so that we can follow what the evolution of the density profile looks like. It's colored by the log r log density slope. So in other words, for an NFW profile, we have -3 between RS and our Veer, which is this pink color, and -1 over here, which would be more of the bluish black color. And so anyway, we can see how this is changing. So I'll throw some tracer particles in there, and right now we're at redshift 1.4 about right here. And so we can see what this is going to do. And so you can see the merger coming in. I'm going to pause it right before this happens. And so, so at this point, all of these properties are going to jump up as the merger crosses into the virial radius of the main halo. You can see that the density profile is sharply peaked here, and that's going to cause a strong response in the scale radius. So the scale radius increases dramatically, shrinks, and then you can follow where the peak in the density profile is due to the splashing back of the incoming halo. And yeah, so, and then we get some additional infalling material piling up along this outer part of the distribution. And so we have material flowing out along this direction and flowing in as well. And we get, yeah, so, and then finally, just I'm going to run through this briefly for a tidally stripped halo as well. So, oops. So for this halo, we've got the region where the tidal force is greater than 1, which just means that its hill radius is, I mean, its the hill radius is equal to its virial radius. We have that's where it's colored red, and then the purple coloring here is also indicating where this halo happens to be a subhalo of another halo. So this one actually becomes a subhalo, is ejected at some point, and is essential again, and probably will become a subhalo again in the future. But for now, we're seeing it like this, and so again we have mass loss occurring in this part of the evolution. And what we essentially see, and this is again typical, is that these halos have a decrease in their scale radius, spin parameter, and shape. They become rounder. And due to just preferential removal of the high energy material from the outer parts of the halo and an overall steepening of the outer density profile. So again, if we look at the particle distribution here, now starting at about redshift 1, so right here, we can see as the halo approaches, so it's going to become a subhalo just shortly here, and then you can see a lot of mass loss from this region of the diagram. The core remains mostly intact, and the recently accreted outer layers of the halo are largely removed. That starts to separate here, and you see the increase in the slope of the outer profile here, which is causing the decreased scale radius. And I will leave my summary up. Thanks.
So there's time for several questions, if there are some. No questions? Well, I'll just say that, okay, David.
When you actually look at the images of the galaxies, do you learn something?
Halos.
But if you look at the images of the halos, did you not include them because they're not informative? Or looking at this way, my mind is struggling, keeping up with all the points and stuff. Just curious, what was your experience in looking at halos as these things collide?
So, well, we haven't exactly done that. Well, I mean, just looking at the dark matter particles, I mean, it's a bit hard. Yeah, we haven't done that much. Yeah.
Observer, I'd be curious to see what they look like with this sort of what you call backslash.
So the pro-lateness parameter is a good thing to illustrate what they look like. So the pro-lateness jumps up. You may have noticed that when there's a merger, it's almost always got a double hump.
Right.
What's happening is that the two halos are coming together, then they slosh around a bit.
Right.
And that's why you get this typical double hump. You see exactly the same thing in X off. That's the difference between the highest density point and the center of mass. Same thing happens. So that's the kind of thing that's happening. Actually,
Yeah, and
Christoph has made zillions of these plots where he's looking at all the dark matter particles. I know he intends to put them online so people can enjoy running through them, stopping.
yeah, and I know there's a lot of information. Yeah, there's a lot of information there, but I think if you just watch it a lot of times, and then it kind of you can absorb a lot of it, and it's probably maybe a little bit more informative than just looking at just the particles.
Full phase space, of course, is 6-dimensional. This is a nice way, I think, to reduce it to 2 dimensions that you can plot, and then especially putting in those colored tracer particles, and then maybe you can see that many of them do this, and that's basically that's the kind of orbit that they have, it's an elliptical orbit. Tom, looked like you wanted to ask.
I said, why don't you show the movie again? But I think there was a feature right at the end there, sort of art.
Yes. Actually, it happens many times, especially after merger. That's just
Are you talking about the second one or the first one?
There was right at the end. There was a movie. There was sort of an art view, large R, large V max.
Yeah.
What was it?
Yeah, so that was after. So this was a halo that was tidally stripped. It was a sub halo, and then it left the main halo and had kind of a tail of material that was just not bound. So that was that was all gray. That was all unbound particles. So those were just some not actually part of the halo, but they were assigned to it from the halo finder, and so that was just material that was kind of being left behind after it stopped becoming a sub halo. Yeah.
After a merger, you see a similar phenomenon, and that's the splashback. Yes.
Is the mass loss always physical, or are there some noise in the halo?
Oh, noise. Yeah. Well, certainly. Yeah. So yeah, definitely. So it's going to depend on the halo finder somewhat. It's going to depend on the definitions you're using for virial radius and mass and whatnot. And in the case of tidal stripping, you're in a really high density region, and so yeah, you could have some noise there. So subsequent runs could give you somewhat different results, but when you're looking at significant amount of mass loss, I mean that's still going to be the case. You'll have a little bit of noise, but so in the tidal stripping case, I think these halos are definitely losing a lot of their mass. In the merger case, things will be different depending on if you're looking at farther out from the halo, for example, and you use some definition that's larger than of the mass that encompasses more than the standard virial mass, then you would maybe see something a bit different. Yeah.
So let me mention that I'm disappointed that Phil Mansfield couldn't come because Andrei Kravtsev, Benedict Emer, Sergej Moore, and Phil Mansfield have been trying to reanalyze big simulations using a different definition of halos, where the halo is supposed to be everything inside the outer caustic or the splashback radius. And so I think we should emphasize that when we talk about mass loss, this just means within, in this case, the virial radius definition. But that material isn't lost. Much of it is still bound. It's just outside the virial radius. The virial radius is supposed to be the radius that encloses material that's virialized, not just the material that's bound. That goes out much further. So it'll be very interesting to see the properties of dark matter halos with this different definition that goes out to a somewhat larger radius. Unfortunately, that talk isn't here, but a lot of that work is being published, and I think they're just finishing. Benedict Emer, I think, is just finishing a big analysis of one of the big simulations. So we can see how properties of halos depend on that different definition, which they argue is a more physical definition than virial or 200 critical or 200 mean density, which are the other standard definitions. Okay, if there are other questions.
As long as I have time, I think you ask. When you look at the stuff that actually escapes as a result of, say, the tidal effects, are the structures coherent? I mean, as observers, we often see tidal tails and things like that, or is it sort of just generically the raw stuff that sort of escapes that's outside of our veer and just all over the place, where they can
we haven't
blobs of things that we as observers might say, oh, we see some extra gas here or something like that. I'm just Again, as an observer, what you
Yeah,
see.
so beyond what you see in the video, we haven't followed exactly where the lost particles are going, what shape they might have afterwards. And, yeah.
How big they are within some region.
Yeah, so we could look at that, but we haven't yet.
Are they ever bound?
Oh, yeah,
Or
sure.
they still stick, they're like satellites that sort of get thrown out?
Again, bound isn't the right thing. Inside the virial radius is the right thing.
No, I mean bound, internally bound, but they stay.
So many of
behind
these
there.
objects that we consider to be outside the virial radius are still bound.
I understand bound to the primary, I'm talking about are they self-binding?
Well, okay, that's an interesting question we haven't looked at.
Because we have
I think we
observers
need to move on to Dushan's talk so we don't get too late for lunch. So let's thank Christoph again.